Okay, so welcome. Like I said, it's a pleasure to be here with you. I'm Christopher, a mentor from the uh, programming and electric area. And here is Sophie with me. Sophie, please. And- Okay,
Hi, my name is Sophie, and I'm part of the area of programming and electricity.
okay. So first we have some recommendations on how to start your programming and your ideas about an autonomous.
Well, as you know, the autonomous period is like the first stage of a match that there are like 15 seconds in which the robot has to work on them own. And Lambot has a main process that helps us to create a good autonomous. Um, the first consideration is to think about the rules and keep them in mind, like the routes allowed, the main points, and all the information that help us to um, be more successful in this process. Now we have to plan the best trajectory. It's important to think about the different ways to move during this period. It's recommended to focus on making the highest punctuation and economize the time. Now, when already have your trajectory, you also have to consider that in certain moments of the autonomous, you have to do specific actions. These actions are based on the way your robot is moving and how you can earn more points. Well, when you already thought on that points, it's time to start programming. And it's important to remark that a really important part of this process is to first plan and then start programming. In that way, you will be like more organized and this process will be easier. Um, Now, the last recommendation is to test action by action. Um, that means that if you have a code with, I don't know, 20 actions, it's important to first try the action one, and the action one get correctly, you can go to the action two. And if the action one and the action two get correctly, now you try the action three, and this one have to work together. And in that way, the code will be like more organized and your autonomous will be more successful. Well, we have 6 types of autonomous. The first one is based on the time the robot has been activating during the match. The robot is gonna perform actions depending on the internal timer that it has. It's easier to program, but in case the trajectory fails, the auto can change the routine. Now we have the encoders. Autonomous that use encoders give more precision to the actions because use the main sensors that the motors of the chassis has in order to know how the robot is moving through the field. Now, you can use other tools such as motion profiling that is similar to encoders, but adding like more information that the like the voltage and the speed that the actuator is receiving. This one answer the questions like where we are and how we are moving. Now, the computer vision works with the elements of the field to perform some actions or move to a specific zone. For example, during the last years, some teams have used the reflecting tape to shooting, aiming, climbing, or to positionate like objects. Now we have the sandstorm that in 2019, there was the option of drive the robot in the autonomous period, but just using the vision of a remote camera. or use an usual programming for the autonomous. The disadvantage of using a camera is that the vision was like a circle, like a eye fish, and the elements of the objects were like dysmorphed. And then the last option is no autonomous. It's included because in many cases, it's better to keep safety in order to avoid damage to the robot or maybe could interfering with the routines from the other teams. It's like play it safe.
Okay, so here just to remark, we have 6 types, but your team can use many kind of tools or many kind of trajectories. For example, the path weavers that first has just add to the materials, but this is just like an example of the main autonomous ways that you can use for your teams. So for example, if you have a time auto, you can add computer vision, or if you have the encoders auto, you can add the path simulators or the motion profiling, so you can like create a more complex auto in order to have like these extra tools that will help you following the trajectories and the actions. So now we go to the parts of the autonomous.
Well, the autonomous have two main components that are path and trajectory. The main difference is that path indicates like the way the robot will follow, like the places, the zones, and the specific point. And the trajectory includes like more realistic elements that are necessary for the routine. For example, sometimes could include components of other tools, such as motion profiling, adding more information like speed, distance, time, and others.
Okay, so now once you have your ideas, you know the rules, you know which actions are uh, more useful for getting more points, you plan your path and your trajectory. From this point, you have great autonomous actions because you already know where you're gonna go. So then you can start adding some tools, like for example, these two main controllers. For the ones that are familiarized with the PIDs, used for also other engineering projects, because it's mainly a proportional, integral, and derivative controller, where you can see how many errors your robot, in this case, is having from the trajectory that, for example, here, the blue line is showing how the robot should move or how the signal of the, I don't know, the voltage should go for a motor. And then the PID is controlling like the movement through time. So you can go to the specific point that you want to achieve. For example, you start here, you want to go to 1. So you move through the time and through the lines in order to achieve the voltage of 1 or the trajectory in the point 1. This is an example of PID that, for example, the new motors, new controllers, and the Falcon controllers use directly in the libraries of their codes. So you can, for example, set the PID directly to the motor and not necessarily program something apart from the main code of the motor. So this can be used for the voltage in your motors, for the positions, but also to the movement of the trajectory for the main road. So this is like a steps where you can apply this specific tool, and you can like use not only for the chases, but turrets, intakes, many things that you need to make the control, or for example, the voltage for certain mechanism. Lambot used it, for example, this year for the turret aiming during autonomous, because we needed to recover the speed after the first ball was shot uh, from the turret. And then you have to recover this voltage that you were using with the first ball. So the second one could go out at the same speed. So that's where we use the PID controller. This is an example because you have a level voltage, then you go down because you have shoot a ball, and then you have to go up at the same start level. So the second ball goes out at the same speed, at the same trajectory. This is an example that you can use, for example, like I said, in your chases or motors. It doesn't matter because the PID is a very useful tool and very flexible for many mechanisms and components. Now, the other one is the motion profile that Sophie had already mentioned. It's based mainly on how your motors and actuators are like uh, moving or working at the real time. So you can see here, for example, the jerk, the acceleration, and velocity, for example, for a motor or a chassis. Then you have the main thing that is positioned here. So you focus on the position or the voltage or the level that you want for certain mechanism. And then you start saying, okay, if I'm in the beginning of the line, I need to go up for the velocity so I can reach a certain speed. Then I have to keep it. And then when I arrive to the point where, for example, for my trajectory, I have to go down because I have to stop in that point to perform certain action. Then you said, okay, now I have the velocity. How are going to work my accelerations? So here we have like the shapes that you are using because from the velocity that you have said, then the acceleration goes up, it keeps when the velocity stays constant, and then the acceleration goes down because you have to start slowing down in order to your robot to arrive at the certain point that you're using. This is a very like intuitive tool because you can see it like here in the graphics with this kind of shapes, this kind of graphics. But in the implementation, you, for example, can use as many complex maths as you want. Let's say this is a position function that uses, I don't know, cubic or polynomial expression, then you can use a derivative maths in order to get the velocity, and then the derivative again to get acceleration, and you go like that. So it's also a very flexible tool that you can use for many cases, and it's very useful when you want a specific information for your motors and the trajectory that you're following through the path of the autonomous. So this is our main two tools that we use for the autonomous in different cases. For example, PID, we use it more for the mechanisms and the voltage of the motors, and the motion profiling, we use it for the chassis and how it's moving through the trajectory that we planned. Now, here is a little sample of how we create a trajectory. As you see here, I don't know, this is the one field from Deep Space 2019. You start here in the 00, and you want to go to the rocket in the center, no? So you first plan the path. How do you want to move there? Then you have to add the waypoints of reference. And then for your robot to follow that trajectory easily, you can smooth that curve in order to get a smoother trajectory and an easy trajectory that, for example, gives you a lot of time instead of going like just squares. It goes with curves and you have more time, and obviously it's a more natural movement. So as you can see here, it's a simple example of how the trajectory that we mentioned before is changing constantly in order to have a better movement through the field. This is also because, as we said before, for the motion profiling, if you had a smooth trajectory, you can create a function that represents that trajectory and then start calculating velocity, accelerations, jerks, or voltage in the case of your motors. So that's why we prefer use these smooth trajectories because it's a natural movement that gives you more time and also more information about how you are moving through the field. And that comes from the planning of the beginning. Now, some parts important for the trajectory is that you have to know how to follow it. There are many ways, for example, the PID in general, the time autos or the encoders, how many meters we have moved. But one option that we have found for us is the looking ahead points. As you can see here, we have a trajectory and then the actual path of the robot and a looking ahead point. This is like a point of the trajectory that the robot wants to reach in order to move through all the specific moments. So, for example, if you had this trajectory, the robot will create looking ahead points to follow that trajectory that goes for a certain obstacles or maybe balls or game pieces. So to create looking ahead points, we have the look ahead circle. That it's the robot is in a position, then you have the looking ahead circle around the robot, and then the circle is touching the trajectory, and then that creates the looking ahead point that we are looking for the robot to follow that trajectory. That is used with the position of the robot and also a programming of where the robot is on the field. I'm gonna mention that in the next slide. But it's basically just saying, okay, I'm here in the field, and then I want to go to that point of my trajectory because I'm like going to another curve or another obstacle. So I detect that the looking ahead point is, I don't know, for example, here in the position 0.5. So I go there and the robot knows the direction that it has to take in order to return to the trajectory or also follow it without any other controllers. And here is an example of the is look ahead way of following. This is more looking like the PID because it has a looking ahead circle like small. So the looking ahead points are closest to the robot and you are moving, always trying to keep on the same curve. That's why we prefer to use the large look ahead because the large look ahead gives you a reference more further in your trajectory, and that gives you the option to have a smooth trajectory depending on the path that you're following. So for example, if you had a very close curve that you want to go through, it's better to use a small look ahead so your robot doesn't lose your trajectory. But if you are, for example, in a large cube or in a complete straight line, you can use a large look ahead points so you can like follow the trajectory without any other for example, interruptions during the trajectory. And that's like the main ideas of how to follow it using look ahead points. That it's why we use like first the path, then a smooth trajectory, and finally a look ahead point to follow that trajectory.
Well, as Christopher mentioned, the velocity is a really important part of the autonomous, and uh, it's almost impossible to be at the same velocity all the time. So the recommendation is that when you are going to start, try to do it slowly at first. Then you increase, and then you keep constantly. And then when you are going to stop, you decrease the velocity and then stop. Um, with that, I mean that instead of the velocity pass from the 0 to the 1 in one step, try to do it like gradually, and this will avoid strange movements. The robot will be no the robot will gain like stability, and the routine will have more precision. Remember that more velocity represents less precision, and less velocity represents more precision. And in the autonomous, the more important thing is the precision.
Okay, so for example, if you have, I don't know, in this year, there was an obstacle on the carpet for the cables that also first mentioned. You have to pass through that obstacle. So you said, okay, my velocity has to go down. So that's why we use velocities to plan our autonomous because, as Sophie said, you need precision. So you have to calculate how fast is going your robot in order to have in mind that maybe it goes out from the trajectory or a certain point that is difficult to follow. Maybe the robot will lose that trajectory. So you can slow down and gain that precision that we mentioned. So now you have your path to follow, the trajectory with the specific elements, your look ahead points to know how to find that trajectory, and you have already considered the velocities that you need in each point of your trajectory. Now, how to find the position of the robot in the field? We use the odometry, that it's like a simple calculus for all the, I don't know, movements during the robot, during the trajectory, sorry. You use the odometry because we have the distance of the left and right side of the robot divided by 2. And then you know, like here in a plane, where your robot is depending on the angle that your robot is rotating. So for example, this is very useful for tank drive or sphere drives because you have the encoders of the 4 or 6 wheels in your chassis, and then you can calculate the rotation of the robot with the pigeon or Navex sensors. So with this information, you can, for example, position it a 0, 0 point in the corner of your driver station, and then said, okay, my robot will start in the point, I don't know, 1, X1, Y2, and then for the distance that the encoders are moving and the angle that the robot is rotating with the sensor, you can calculate where in the field, depending on the first point that they started, is your robot. So that's very useful to follow trajectories, especially in the drives that have more encoders in their wheels. So this is a very useful tool that we used during the last year. So you can like know where you are in the field and how you're moving, because once you have your position, you can calculate in that specific moment your velocity and your acceleration, and if the robot is going through the trajectory that you specified or it's moving through another part. So this is very useful because it gives you information. Obviously, when with the time of the autonomous, it starts like changing a little bit the true values, but it's very useful for the precision that you want to follow trajectories. So here are some examples of implementations of the trajectories. During 2018, the Power Up Challenge, we used these smooth trajectories with odometry for a robot that it's here. It's on the Blue Alliance. And the auto was to take these boxes, the power cubes, and put it on the center. So here we use a trajectory to follow. So as you can see there, the robot was following the trajectory, then goes for a gain piece and then return. There are many elements that you can control, but this is the main idea. For 2019, as Sophie said, we have in this space a lot of, for example, you can see here reflecting materials, also here in the center rocket or maybe in the human stations. So that year we decided to also use a Mecanum drive implementing computer vision with the Limelight, that if you see in this robot from Lambot that it's in the red lines, we use the green lights to uh, locate these the reflective materials, and the auto goes for that specific points to finish the actions. Here it is. So as you can see there, the computer vision helps us to locate the positions that we have on the field, and also the objects, or maybe, for example, in that case, the places where the disk goes to put, and the robot needs to do the action. Then in 2020 and 2021, we discovered this that is adaptive prior pursuit controller from the team 1712, and we implemented in on a simulator for Unity using some ideas from the path weavers. So we create the simulator in Unity using this adaptive prior pursuit controller, and as you will see here, the autonomous was a lot precise on the trajectory that it was following, and also we can like plan our paths or trajectories and movements in the simulator without any robot. So that gave us a lot of advantage because our mechanics team could be working on the robot and we planning in the auto with the simulator. That was like very similar to reality. So here we go. And there is a trajectory with the green points, and then the actual path with the pink color. Okay, so that is the main idea. That year we use a tank drive using the adaptive preprocessor controller, motion profiling, and also the path generation generator on the Unity simulator. So as you can see there, the simulator gives us the idea of the trajectory, but obviously during a match, there are many elements that you can control. So in a certain example, it didn't complete the trajectory or maybe stop before in order to keep the safety of the road. Now, in fast ideas, for rapid react, we have 15 seconds of autonomous period. And as we said at the beginning, there was a rule where human player can shoot balls from the human station to the hub. So well, during just the autonomous period. This information is very important because you can plan different autonomous depending on what you want to do. And for example, for our first autonomous, we started going like in the starting position, then goes from this ball, next one, and finish there because we were planning that our human player will shoot the balls to the hub. So that's like an idea of how you can implement the rules to your favor and give, for example, many options to other teams that are in your alliance. Then we change our auto. We have some examples here of how to follow in the trajectory. For example, this one, Lambot is here, the back, and it will move like for these walls once we have planned that trajectory. So as you can see here, also we use vision this year for shooting and aiming in the hub, and our chassis was a Mecanon drive. Okay, so that is an example of one of our paths. As you can see, the chases didn't move like we expected because the last ball that it's here in the human station, we cannot reach it, but it's a difference in the movement of the road. Here is another example at a short trajectory and aiming directly to the hub. Here is the robot of Lamb. So as you can see, we have two different autonomous, so that it's one of our next recommendations. So to finally finish, we have some general recommendations. The first one is to be patient because many times we tried, like Sophie said, 20 different actions, and then we don't know where the auto is failing. And we said, okay, we are having many mistakes, but we don't know exactly where. So first, be patient. And then keep it simple because you have to think on the main actions that you have to achieve, how to keep your robot in the trajectory. Also, have in mind safety because you have to learn that your robot could go further in your autonomous or maybe touch field elements that maybe can damage even human players or your robot itself. So try always to have a safe auto so you can keep the integrity of your robot and also from the people that it's around. Do many tests because it's very important to be 100% sure that your auto will work, not just for the integrity of your robot, but also the playing team with your alliance. So if you said, okay, I have an auto that goes just straight, and in the last moment it goes curve or it turns right, left, and interferes with the autos from your alliance, that's a problem. So maybe you have to do many tests to do exactly what you want the robot to do during your auto. And as you say, as you see in the last slide, different autos is very recommendable because, for example, Lambot had an auto that goes for the first ball in the right side on the field, and the other auto that we showed at the end that is just going for one ball straight. So that gives you many options for your alliance and many options for you to plan different strategies during a certain period of the competence during competition. So for example, we had an auto of do nothing because maybe we needed to stay still during the start of the match, or an auto for that shoot just one ball, two balls, three balls, five balls, and that gives you like the option of doing many actions, have a more flexible participation with your alliance, and obviously the the contest with every match. So this is our recommendations for you. And now I guess we are open to questions, no?
Yes, absolutely. Well, first of all, Christopher, Sophia, thank you very much for being here today. And yes, we're open for questions, everyone, on the Q&A section of the webinar. And we already have one question for you, and it is, which language, which programming language you use for coding?
Okay, so we use Java, the last version, 8.1, I guess, because it's more flexible for us. We work in the Visual Studio with WPLib. We have tried once LabVIEW, and also it works, but it's like, I know that it's different from Java, but we use this main language just because it's like more flexible in our methods that we want to use, and also because it's one of the codes with more documentation in, for example, Chip Delphi or the WPLib docs. That's why we use that language program.
Okay, thank you. And the next question is, at what time or in what moment, I guess, of the season you decide your strategy or define your autonomous trajectories?
Well, this is very curious because at first you don't have a robot. So you have to think just like you are gonna move through the field. You said, okay, maybe during the first 3 days of the kickoff, you said, we will have this mechanism, we need to do this action. So you said, okay, I have a robot, obviously have a chassis. Then, for example, during the previous session, we know that we will use an intake and a shooter. That's all. So we said, okay, what can we do with a chassis, an intake, and a shooter? Okay, we see the image of the field and then said, okay, I go for this game piece or this other game piece. So we decide first during the first week how the auto is gonna move with the first elements that we have, just planning, like Sophie said, a path to follow, some little ideas. But the main work is when during the third or fourth week of the season, because there we said, okay, we already know all the rules. We already know that a robot how should be designed or how should be working, even if we don't have a robot. And in that point, we start planning how a robot is gonna move. So for example, for the first regional, we have one auto, and then that we tested on that regional, we said, okay, that worked, that doesn't, and we change it, for example, for the second regional. So between the third and fourth week, you have to start thinking more exactly what actions you are going to perform with the mechanisms that supposedly you are planning with your team.
All right, thank you very much. And we still have more questions in the Q&A section. Unfortunately, we ran out of time, but if maybe you or Sophia could stay and answer them via text on the Q&A section, that would be really awesome. And again, Christopher, Sophia, thank you very much for being here. We really appreciate you taking the time to give us this presentation about your autonomous and how you work with that in Lambot. So, well, thank you for being in warm up, and hopefully we'll see you next year.
The pleasure is ours, guys. Thank you for the invitation.